Park, UNIS Korea. I'm chairing this session. The first speaker of this session is the Professor Nicolas Ferre. He will talk on the QMMM interface between the electronic structure and molecular mechanics. Let's welcome the speaker.
Thank you very much. Do you hear me correctly?
Okay, very good.
Yeah. Perfect, thank you.
Mm.
So first of all, of course, I would like to thank the organizer. Of course, I would have preferred to visit Korea, but hopefully in the next year, I will visit. So today I will discuss a little bit further after Michael Rutland's presentation yesterday about our QMMM program. And I will maybe focus a little bit on some technical issues that we would like to tackle in order to run really large molecular simulations. So first of all, I would like just to remind you that in the QMMM approach, we need to merge two different visions of what is molecular modeling. On one side, we have quantum mechanical methods, especially for electronic structures. So many different properties that can be obtained through these QM calculations, like for instance, UV visible absorption spectrum or an infrared spectrum or reactivity. And on the other side, we have molecular mechanics and molecular dynamics simulations that give access to many different properties, usually dynamical one. And so the big question for me is how we can merge these two points of views. From the coding point of view, there are different ways of integrating this QM and MM point of views. The first one, the obvious one, is through a single package, whether QM or MM package, but where you want to implement extra functionalities in order to reach this kind of QMMM approach. Unfortunately, in that way, we can never hope to have a full picture of what can be achieved by means of QM or MM methods. Another way to do that, to achieve that, is to just minimize the implementation, the coding into each of the MM or QM packages. And so you have to focus a lot on the driver. So a small piece of code that would help to interface the two packages. But in that case, you can imagine that driver implements just a subset of functionality that can be found into the MM or the QM packages. So this is the reason why we have chosen to base our QMMM development on two packages and make them communicating as efficient as we can, hoping for the best of two worlds. When you deal with the QMMM approaches, the first thing you have to do is, of course, to write down the equation for its energy. And most of you have often seen the standard way of having the QMM energy as written as the sum of three components: the energy of the QM subsystem, the energy of the MM subsystem, and then the coupling between the two subsystems. But here I would like to adopt a slightly different notation in which the total energy depends on both the coordinates of the atoms, the atom coordinates in the QM region with this R, and in the MM region with this tilde R. And so I will show you how we can write down this total energy as a sum of two components. The first one, which is a QM energy, so meaning that this contribution is calculated by means of a QM calculation, which depends on both QM and MM atoms. And on the other hand, you also have a contribution coming from the MM package. So if I introduce the ESPF QMMM electrostatics method we have been developing over the years, and the method that Michaels has shown you yesterday. If you remember, the central quantity is actually an atomic charge located on a QM atom, which is just calculated from this equation, in which there is an expectation value of a QM operator, a charge operator QA. Okay, so on the basis of this definition, then you can write down the total energy as I said, as a sum of two components, a QM and an MM ones. And so I write in blue the terms that are calculated by the QM package, whereas the red ones are calculated by the MM package. So of course, as usual, you find the first terms that comes directly from a QM package, where H0 represents the gas phase Hamiltonian, more or less, in the calculation. And then on the other side, you have the red one, only written in red, which represents all the terms, the classical terms that are calculated by the MM force field, which here are non-electrostatics. And at the interface, from the electrostatic point of view, you have this term in which all the QM charges are interacting with the external potential driven by all the MM charges. I really would like to emphasize that these charges are not fixed. They are really polarized by the MM environment thanks to this term. And because this actually charges are based on charge operators that enter directly into the one electron Hamiltonian in the QM package. So good, so far so good. So if you want now to derive gradients, for instance, for geometry optimization or for running molecular dynamics simulations, then you have to consider two kinds of derivatives. The first one with respect to a QM atom, and the second one with respect to a MM atom. So we can use usual tricks that exist for a very long time in the QM methods, especially if your QM method is variational with a single reference, for instance. And you can retrieve this kind of terms on that line. On the other side, you will have also some derivative with respect to QM atoms for classical terms. For instance, if you have some van der Waals interactions, or if your QM and MM subsystems are bonded by covalent atoms. And then you have the electrostatic interaction terms. There are two of them. The first one, which involves the derivative of the atomic charges, of the QM atomic charges, interacting with the external potential, and the other one, the obvious second one, which correspond to the interaction of the charges with the derivative of this external potential, that is the electric field. For the derivative of the energy with respect to an MM atom, the situation is much simpler because it reduces to just two terms. But in any case, at that point, you have to ask yourself, for all these terms, which one should be computed by the QM package and which one should be calculated by the MM package. The option we have chosen is really to restrict everything that can be done classically inside the MM package. For instance, here on the electrostatic interaction term, the term in which you just stick with the QM charge will be calculated into the MM package. So we can make a clear separation between the terms on the left, which are calculated into the QM package, and the ones on the right side, which are calculated in the MM package. And thanks to that splitting between these terms, the communications which are needed between the QM and MM programs are really restricted. On one hand, the QM package needs to give some information to the MM1, for instance, the positions and the atomic charges of the QM atoms. And on the other hand, the MM program just have to send the value of this external electrostatic potential to the QM package. So you can imagine that the amount of information that has to be exchanged between the two packages is reduced. Now, if you go to the second derivatives, the situation is a little bit more tricky as usual with second derivatives. I will not get into the details because Michael has presented that yesterday. But similarly to the gradient, we can split the effort into some pieces which have to be calculated by the QM package and some pieces which have to be calculated by the MM package. So this is where the green lines make the separation. So now from the point of view of information exchange between the two packages, the situation is changing a little bit. Still, the QM package has to send to the MM1 the atomic position and charges of all the QM atoms. So nothing really huge there. But for the MM package, if you look at the equations on top of the slide, you see that now you have to send not only the external potential, but also the external potential derivatives, both with respect to the QM atoms and to the MM atoms. And now this last term is quite large because its size is the number of QM atoms times 3 times the number of MM atoms. So imagine if you want to model some realistic protein or embedded into a membrane, taking into account the solvent, this number of the size of these derivatives of the external potential can be really, really large. And as a matter of fact, our way to make a connection, the communication between the QM packages we have chosen, which are Gaussian and open Morcas, and the MM program, which is Tinker, is simply based on ASCII communication files. This is the most inefficient way of doing communication between two packages. But think a little bit about that. On one side, we have QM packages with their own way of dealing with communications. On the other side, you have the Tinker package, which has also its own way of dealing with this kind of communications. This is really complicated to make them communicate because they are not using the same languages. They are not using the same conventions. For instance, in a QM package, usually you are using double precisions, whereas for MM program, it's usually done in single precision or in mixed single and double precisions. So it's really hard to make them directly communicate if you don't use some kind of ASCII communication file. The cost, the price to pay for such a choice is obvious. The size of the communication files will increase a lot with the size of the system. For instance, if you see this box of water molecules in which only one single water molecule is treated quantum mechanically, whereas the remaining ones are treated with a force field, and you increase the size of the Hessian calculation you want to perform just by using a radius around the QM subsystem, then you see that the timings of the calculation increase exponentially for sure. The main communication file, the one for the external potential, does not increase much with the number of MM atoms, but the one with respect to exactly the Hessian communication file is increasing also exponentially. So we know we have to deal with that, and we have a couple of ideas how to solve this kind of trouble. But for now, I just would like to mention also two different ways of dealing with this interface with between the QM and the MM programs. whether in any case you have to make some kind of interface program. For instance, this is in our case when the quantum mechanics code is the master program. There is a program called TKA2QM_S, which is actually a standalone program. Okay, so you can imagine that at some point this standalone program just needs to deal with all the initialization of variables and stuff like this before to run into the calculation. So these are some advantages. It has some drawbacks, of course. Another way of doing that is just writing an application programming interface. So in that case, this TKR2QM can be actually this kind of API if you can think about a correct module that would implement all the required elements for this kind of interface. Of course, this has also some advantages and also some drawbacks. So if I compare these two approaches, the standalone program and the API, in one case, in the case of the standalone program, Tinker is really a program on its own, meaning that the quantum chemistry code needs to make some system call in order to run it separately. So as we have seen, we need some communication files between the two programs. And of course, one of the major issues is that actually the memory space for each program is separated. There are no communication between them. And so you have to be careful when you want to allocate enough memory for having both programs running simultaneously. In order to improve the communication efficiency between the two programs, of course, we could go for a better format than ASCII, and HDF5 is probably one of the best at the moment. But again, we have to be sure that the QM and MM packages are able to use this kind of facility. So on the other side, there is the API. So now Tinker has to be seen as a library, meaning that you can manage with direct call to this API. The memory is shared, which is a good point, meaning that we don't need any more communication files. But you may imagine that some memory requirements can overlap between the two objects, the QM and the MM objects, that could make some trouble. And one issue that actually I never found a really regular, efficient solution is because we are developing our interface on two existing packages. In some cases, they can share some object names, exactly the same object names. So of course, at compilation time, you can trick a little bit some function names, some subroutine names, adding, for instance, an underscore character or stuff like that. But I don't think this is really efficient, especially when you have to deal with these very large existing packages.